Everybody, please welcome Iván Sánchez. He gave a great talk yesterday, a practical session around using LLMs, and today he's going to share some of the details around what Zyte have been doing in the last year with LLMs, diving into practical details and sharing some of the results. Please give a warm welcome to Iván.
Thank you, Shane. And does it work properly? Yes? So I'm Iván. I'm data scientist at Zyte. And in this talk, I am going to show you some stuff that we're doing at Zyte related to using large language models for data extraction from the web. In particular, how we're working in optimization of the inputs for the LLMs, how we are evaluating these LLMs in this particular niche task, and also some takeaways and some conclusions we took along the path when actually fine-tuning our own LLM to perform these tasks more efficiently than the ones that you just get when you download some open source LLM. So in general, what am I talking about? What am I saying when I say we are solving this? What is the general idea of solving this task of data extraction with an LLM? And actually, the underlying idea is pretty simple. You just grab the page text or the HTML from a website, and you take the schema from a user explaining what data you want to extract, and you just put that into an LLM, and hopefully the LLM will generate the answer with this extracted data. So the general idea is very easy. But why would we even want to use LLMs for this task? Like, we already have countless number of software or libraries already scraping sites, and we have the classical scraping methods that rely on the selectors and regexes and everything. Why do we even need an LLM, which is such a powerful and expensive technology, to solve this task? So actually at Zyte, we have so much exposure to different customer needs and related to scraping different information from the web pages that we saw there's a tendency right now that since we're solving already the problems that are easy, there are new problems raising in these customers that they want to extract data that maybe it's not even in the page that has to be generated, or maybe that it's in general very hard to scrape. And also, I will be showing here a couple of examples to make a point, but also one of the things that the LLMs give you is that they allow you to go one step further and have some no-code extraction and normalization of data. So it's really a game changer in the terms of understanding the context of the page, and we really want to use this. So just as an example, I'm going to show you a couple of examples. Here's a page and an actual use case from a customer. This customer wanted to extract the weight of the items from a different array of a lot of different domains. And we saw there were several domains. In this particular example, you can see that, I don't know if you can see that properly, but it's just a table. And in the row of that table, you can see package dimensions. But in the same row, you have some weight. And as humans, we're very robust, right, to this kind of noisy information. Since it's talking about the package here, the package dimension, and it's a number that contains some unit of weight, we very easily understand that this is referring to the package weight. But to solve this problem, or to extract this information with classical scraping techniques with some selectors or some rejects, it's incredibly hard. And because you have to do, you can do it very easily for this page, but what if you want to do this for 100 different domains? Probably you will need some QA person there checking that it's not being extracted correctly, and he will need or she will need to create some particular code for this particular example. It's very hard, but for LLMs, this is also super trivial, and this is a game changer. This is what we're trying to these are the kinds of problems that we are aiming to solve when we say, okay, we're going to use LLMs for this task. And as another example, this is kind of different. This is from a customer. They wanted to know whether a product had free delivery. And in this particular example, you can see that, and this is the only mention whether this product is free or not, was just in an image. So there was no other mention in the page that the product had free delivery or any other mention about the delivery price. And this is another example why LLMs are very useful for this particular task, because in the HTML of this page, you will have the alt text of this particular image. So you don't even need some vision capability, which also LLMs can give you, but just some text LLM is able to understand that since the alt text of this image has something like free delivery badge or something like this, it has the reasoning ability to say, okay, since you have this badge in this page, I'm going to assume that the delivery is free. And we saw that there are a lot of customers that, have maybe one or two attributes that are very hard to extract, like these ones. And in general, we analyzed all the different attributes we get requested, and there's a very long tail of these use cases that we would like to solve and be able to solve for the future. However, using LLMs to solve this task doesn't come without challenges. And the obvious challenge is that web pages are super long, they're super big, and they usually contain a lot of information that is not really relevant for the extraction tasks. So when you want to extract the price from a page, or whether the examples that I just showed you, you don't really need all the information the HTML has. So sometimes the HTML will contain comments, or they will contain stylings, or some scripts, or the notes will contain, the tags will contain attributes that don't really add anything, and actually they make the problem harder to solve. So one of the optimizations that we are using to be able to use LLMs to solve this task more cheaply and more efficiently is we're removing most of the information from the HTML that we understood, and we did an analysis for this, that it's not really necessary to do the extraction task. So as I said, we're basically removing a lot of tags that are not relevant, and then they don't contain the information. And also we're stripping out a lot of attributes, and we're doing some node merging without really destroying the information that the HTML is giving you. So for example, we are keeping particular attributes from nodes that we consider they're important to extract. So a lot of clients will come and say, I would like to extract the URLs for a list of products here. So for example, we are keeping the href attributes from the A tags. But they're very little, and I will show you later how much we're improving the cost or the usage of the tokens for using this particular optimization. But we don't only stop here for this optimization. We also have some other kind of optimization which selects, so we have a model for product, article, job posting. These are the standard schemas we use at Zyte. So underlying, we have a model, more like deep learning, classical kind of model that selects the main region of the website that says the product information, it's very likely to be within this part. And we're actually using the output of this model, and we are putting the text that we extract from this main node that contains all the information to the LLM, and we are also reducing a lot the number of input tokens thanks to this optimization. Yeah, this is, let me point out the y-axis of this chart, of this box plot, is logarithmic, which means it's growing a lot faster, so to speak, than a linear one. But I just put it like this so that it can be seen more easily, because otherwise the box you see on the right would take most of the graph. But this is a chart that shows a comparison of the number of input tokens given we use or not these optimizations that I just mentioned. So the box you have on the right, it's counting you see the number here, it's the median number of input tokens that we are inputting to the LLM if we don't use any of the optimization. So it will be the full page and all the tokens without optimizing the HTML. So it's showing that the median number of input tokens is 140,000 tokens. That's just massive. It's too much. Like, for context and to understand how much this is, OpenAI models right now have a context window of 128,000. So the median here is already out of these bounds. So this is something we really can't work with, and it's pretty obvious. So just applying the first optimization that I mentioned, so cleaning the HTML already brings down the median to 10,000 tokens. That's much, much better. And it's going to be cheaper. It's going to be a much easier problem to solve for the LLM. So it's not only the cheaper aspect, but also the performance will improve. But right now I'm not mentioning that. And if we go one step further, and not only we apply the first optimization of cleaning the HTML, but we also select the region, we go from 10,000 tokens to 3,000 tokens median. So that's already much, much better. You can even use some smaller LLMs that have more limited context window. Like for example, the older Llama, I think it was Llama 3, originally only had 8,000 tokens. So you could even use that kind of model to solve this task. And yeah, I mean, this also applies when we only use text. So yeah, that's on the optimization part. Now that we have solved how we're going to make it cheap, we were facing the problem that we really don't know how well our LLM is performing for this particular task. So imagine that you have some data that is annotated by a human, and then you have some data, and in this case, data I'm referring to the extraction. So it's a actual JSON of data that can be nested. You know, it can have arrays of objects. How do you compare the one that you extracted with the one that is annotated by a bigger model or by a human? And this task is actually kind of hard, because you can have, for example, for arrays, you can have that your ground truth. When I say ground truth here, I'm referring to the one annotated by a human. You can have the array for the ground truth has 5 elements, while the prediction has 3. So you need some matching there, because also the order can be arbitrary. I will show you an example of what I'm referring to here, but also you can have some extracted attributes, or more like generated attributes, that it's very hard for them to match. They will never match. So for example, if you have a summary from an article, you can pretty much say the same with different words, right? So if you try to match the strings completely and exactly, you will basically never have an exact match, but you can have 2 summaries that basically say the same with different words. So we needed some kind of, way to say this is not completely correct, but at the same time it's not completely, wrong. We needed something that is not hit or miss. Let me just show you an example. I hope you can see this properly. So this is just an example of an extraction to the right, and some ground truth to the left of some extraction from an article. So we have the author, we have some summary of the article, we have some comments. And for the ground truth, you can see that there's like John L. Doe, while the extraction is only John Doe. So when we tried to perform exact matching, this would be a miss. But me as a human, I would say this is not completely wrong either. I mean, it's not completely right, but at the same time, it's not completely wrong. So we actually needed something to be able to assess this, because we had 2 different LLMs trained, and to the human eye, one was much better than the other one. But if we were using a very simple metric for that, we were receiving the same final metric for these 2, and there was definitely a winner here. So we needed something more granular. So one of the, and by the way, asking an LLM how many R's there are in the word strawberry is not a good method to evaluate it. So jokes aside, here we were using, one of the things that we were using is Rogue. So Rogue is basically what takes the tokens from the ground truth and the tokens of the prediction, and it compares them. And just in this example, you can see that the final metric, which is important, is the F1, which is the F1. You can see that the value here is 0.8. And this is already telling us that this is not completely wrong. And this is one of the building blocks that we're using to compute the final metric, given 2 different extractions. Another one, I won't be going through it because it's like a lot of text, but it captures the idea. This is from the summary. So we have the ground truth summary, and then a correct one and an incorrect one. And for these long strings, summaries, chain of thoughts, sometimes even translations, like you can do extract and translate on the fly. You will never, what you have to do here is understand semantically what you have in the string. And by doing so, you can then compare with and have a final number that tells you how semantically similar is this to the extraction like the extraction from the ground truth. And this is what we're doing here. You can see that the correct one has a value of 0.77, while the incorrect one has a value of 0.5. And this is enough to have an assessment of how more similar this is semantically to the other one. And again, this is just a building block we're using, and with this we're building the final metric. And for lists, it's pretty much the same, but you have to work with an arbitrary number of elements and some. You can have different number of elements from ground truths to the prediction. So for this, we're just using solving the assignment problem. In this case, we're trying to maximize the similarity. So we're just building like a matrix, in this case 3 times 3 matrix, and then solving the assignment problem, which you can solve very easily with SciPy to obtain the metric between the two lists. So once we had solved the problem of optimization and the problem of the evaluation, we started training our own LLMs, and we actually trained several. We started with Llama 2, I think. We tried Mixtral. I think at some point, yeah, a lot of open ones. We're actually using Llama 3.1 8B. Hopefully soon we will be using 3.2. One of the things that we saw is that for open source, like smaller LLMs, because we're using the 8B one, which is a good trade-off between speed and capacity, is that fine-tuning really leads to a much better performance improvement than in-context learning. And by in-context learning here, I just mean that giving the LLM some examples of the task that you want to solve. For these model LLMs, it's not so powerful. They don't really understand so much this, and it gets very complicated very soon with the instructions. So it's much better to do the fine-tuning to, make them understand the task that you're trying to solve. And a very interesting detail is that with very, very few examples for the data extraction task in this case from plain text, and by few examples I mean less than 100, we already see a very, very big improvement in how this particular LLM solves the task. Yeah, obviously, the more data you have, the better. But for me, in particular, it was very interesting to see that you don't really need so much data. Like you can spend just some day annotating data manually, and you would already have a very good baseline with an open model. What I also saw is that for more complex tasks, and for example, for extraction from HTML, not from text, but from HTML, which can get very big and more complex, we can still see a lot of improvement after the 300 samples. And at the beginning, we were trying to train with some data that was synthetically generated, and we were doing some things here and there to try to, generate some examples automatically. But we saw, and this aligns very well with a paper that I pointed out here, that it's better, and this is very counterintuitive, because it's better to have little data that is very high quality than having a lot of noisy data. And I say this is very counterintuitive because in classical deep learning, it was it was completely different. It's more robust to noisy data, and the rule in general was to put as much data as you can, even if it's noisy. It's very robust. But with LLMs, and in particular here, I'm talking about performance fine-tuning, so using a LoRa on top of the LLM. It's really important to have high-quality data, better than a lot of data. And another thing that we saw, especially when we went from using LLMs to extract from text, but to extract from HTML, and we started using much longer sequences, is that the effective context length of LLMs is much, much lower than the theoretical one. So, and this also happens for the big ones, right? So OpenAI, for example, the models have 128,000 tokens, but if you try to solve this task of extracting from HTML, you will very quickly see that from some point around the 16K or 32K that the LLM starts performing worse. And there are actually some experiments here. I'm actually pointing out a paper here that does this analysis, like at what context does the LLM start performing worse? And with, for example, Llama 3.18b, it also happens that from the, for example, more or less at the 8K, it starts performing worse. The good news is that we can also improve this via fine-tuning. The only problem that we saw is that to train with long sequences, and by long I mean like 70,000 tokens, you need to do some, if you, for example, you're using transformers library, you would need to use some tensor parallelism, which is like splitting the model into 2 different GPUs or more, and then train like this, because you don't have enough memory in the GPUs to fit it. And that's a problem because it makes it very hard. If you try to set up some 0, 3, which is also another method to put some stuff from the training into disk to make it available to train for all these big context in one GPU, you will see that it's very complicated to set it up. But the also good news is that there's a library that we are using. It's called Unsloth, which allows, it's a piece of magic, this library. It allows us to train just using one GPU and super long sequences, and we're talking about 75,000 tokens in just one GPU, and we're using like 880 gigabyte GPU. And all of this work made it possible to put into Zyte API the custom attributes extraction, which is basically you indicate in Zyte APIs with natural language and just with a JSON schema that you want to extract this data, and that is enough to tell the underlying LLM that you want to do this extraction, and the LLM will be checking at the text of the page, and it will perform the extraction following that schema. So some conclusions in general is that tasks that were very hard like 3 years ago or they're directly impossible are becoming super trivial to solve with LLMs. And whoever won't be using LLMs is gonna, fall back in these techniques, and it's something that everyone, is using already or will be using soon enough. The only drawback is that right now they're too expensive to run at scale. So for example, if you want to scrape using an LLM from 1 million web pages, it's definitely something too expensive to run. However, and this is just a hot take from me, but I guess a lot of you will also think the same, is that running LLMs is going to be more normalized, and it will become cheaper in the future. So for example, we will get better architectures and hardware. For example, we have right around the corner the Blackwell architecture from NVIDIA, which they already reporting that they will have a lot, like more than 50% improvement in the time they take to train and to run inference with the models. And we will also get better models that do the same with fewer number of parameters. So in this case, for example, literally 3 days ago, there was a paper from Microsoft. It's called Differential Transformers, which show a very interesting and promising approach to a different approach to calculate attention in the transformer architecture, that they show a very big improvement in a problem that's called multi-needle in a haystack, which is super similar to the problem that we're trying to solve here, which is the extraction from a web page. Multi-needle in a haystack is basically you have a very long piece of text and you want to extract or pinpoint some details given your prompt. Here is basically the same as we're trying to solve. We're telling the LLM to extract from a big web page information that is here and there and there. So all of this is pointing to the same direction. This is going to be something that everybody will be running because it will become super cheap. Another take that we took is that having a trustable evaluation method is necessary to understand where we are at for this particular task. So if you don't really have a valuable method, you can't, all you can do is just check here and there if it's performing better or worse, but you don't really have a metric. And if you want to be competitive, you need to understand where you are at and how you compare to this model. For example, if tomorrow Google comes and open sources some Gemma model, how do I know that I have to stay with Llama and not take this Gemma model and try to fine-tune this Gemma model? So having this evaluation metric is super helpful to understand that this model can be a game changer here and there, especially when using open ones. And in general, another important topics that are becoming more relevant in the LLM space are the code generation ones, because also it's super cheap. If you can have the LLM to generate the code to run extraction, then you can just run this code for the web pages, and then you don't call the LLM anymore. So that's very cheap if you can pull it off. Also, in general, vision LLMs that can also understand images and layouts of web pages are super relevant, and also they're becoming very relevant in the open source space. And yeah, reasoning LLMs, like the latest model from OpenAI that has so much hype around is this O1 model, which basically incorporates in a hidden stage some chain of thought that makes the LLM or forces the LLM to think before it speaks and spits out the answer. So this is also something that everyone will be investigating and trying to put it in their LLMs. And also agentic LLMs is also a very hot topic, because it's like you have an LLM which has all the brain power, but giving them the ability to act and giving them tools to interact with the environment, with browsers, it's also going to be super relevant. And the first company that achieves some scraping bot that you can just type, I want this and that, and it does everything. Like it goes to this web page, or it can, self-correct or retry stuff when it gets it wrong, and it understands that it makes it wrong. It's going to be a game changer, as I said. And in general, thank you everyone for listening to the talk, and I would be super happy to answer any questions you may have.
A couple of quick questions. We don't have a lot of time. Does using LLMs in data extraction present any new issues besides the cost? Like, for example, like hallucinations in the data?
Yeah, definitely. Hallucinations are I would say, the biggest problem that you have when extracting. Because, for example, one of the problems that can happen is when you extract from a product, that the product doesn't have a price, but in the text the text contains the price from other products. And when you ask the LLM to try to extract something, it will always assume that this information is in the text that you're providing. This is actually a very relevant problem that everyone's trying to solve.
And how did we solve it, or did we?
Yeah, one of the things that, for example, one of the optimizations that I showed that tries to select the main part of the page is to make the problem easier. And the easier you make the problem, or the more filtered information you give the LLM to extract from, the less capacity you will have to, or the less likely it will be to have hallucinations. And another task or another way to improve it is, as I showed, some doing chain of thought and making the LLM try to think and understand the layout and the problem at hand to try to guide it more. And maybe after the extraction also do some self-correction, but this obviously makes it more expensive to run.
Makes sense. So what process, library, or tooling are you using to simplify the HTML?
So we're using HTML text, which is an open source library also developed by Scripting Noob's Zyte. And after several iterations, we tried also Beautiful Soup, but it was too slow in general to run. So we're using HTML text and then some custom code to do some things here and there.
Thank you. I think we'll wrap it up there because we're out of time, but thanks very much, Iván. That was a great talk. And we're going to take a 30-minute break. We'll see you back here at 4 o'clock.